let's take a look at another example. As always with the examples, I would encourage you guys to try to pause the video, work through them, or at least set them up by yourself, and then come back to the video and see how we work through it here. So in this example, we're given two vectors, a and b, and we want to find the angle between the two vectors. So ultimately, we have a couple different options here. We can either use our dot product or we can use our cross product. And in this case, I'm going to show you how to use both. So let's first look at our dot product. So for our dot product, what we can do is we know that we have a dot b is equal to magnitude A, magnitude B times cosine of theta AB. And of course, theta AB is what we're looking for, the angle between the two. But we also know that we have A dot B is equal to AX times BX plus AY times BY plus AZ times BZ. And so what you can see we're leading up to is we can set these two equal to one another because they're both equal to the same thing, the dot product of A and B. So what we can say then is that our AX BX plus AY BY plus AZ BZ is equal to AB cosine of theta AB. And of course, the only unknown here now should be that theta AB. So first of all, let's find these magnitudes A and B. We can pretty easily pull out our x, y, and z components for each of our two vectors, but let's find those magnitudes A and B. So we can say A is equal to the magnitude of our vector A, which is equal to the square root of the sum of the squares. So for A, we have components 3, 4, and 1. So we're going to have the square root of 3 squared plus 4 squared plus 1 squared. And so that ends up being the square root of 26. Similar thing for B, so we can say B is equal to the magnitude of our vector B. We actually only have two components for B, 2 and negative 5. So our magnitude of B is going to be the square root of 2 squared plus negative 5 squared, which is equal to the square root of 29. Now for our other components, of course, we can look here. We have AX is 3, AY is 4, AZ is 1. BX is 0 because there's no u of x here. Our BY is 2, and our BZ is negative 5. So for those, we're just going to plug directly into these values here. So doing that and sort of at the same time rearranging to solve for our cosine theta AB, we have that cosine theta AB is equal to, now the numerator is going to be all of these terms here. So our AX times BX is going to be 3 times 0, plus our AY times BY is going to be 4 times 2, and plus our AZ times BZ is going to be 1 times negative 5. Now in the denominator, we're going to have our two magnitudes, A and B, which we found earlier. So that's going to be square root of 26 times the square root of 29. If we plug all of that in, we get that it's approximately 0.109. Now, of course, if we're looking for this angle theta AB, we want to take the inverse cosine of that. So we can say theta AB is equal to the inverse cosine of 0.109. And if we use stored values, that ends up being approximately 83.728 degrees. So there we found our angle. And sort of as a double check, what we can do is we can sort of think graphically, what do these two vectors look like, and does that number make sense? So I'm going to attempt to draw that here, but we can always use a program like MATLAB to get a more exact drawing. So here's our right-handed coordinate system, Cartesian coordinates with x, y, and z. So for our A, we had a component of 3 in the x direction, 4 in the y direction, and 1 in the z direction. So we have something that maybe looks like this. And so that's a pretty terrible drawing, but kind of imagine that coming up above our xy plane a little bit. So that would be our vector A. Now for our vector B, we know it has 0 x component, 2 y component, and negative 5 z component. And again, these are just sort of rough sketches, so we'd have it looking something like this. So this would be our vector B. So we can see that, yeah, that's roughly, 80 something seems like a good approximation for that angle. Again, to get a better view, you would want to plot that in something like MATLAB or a similar program. So let's now briefly look at how we would solve that same problem using our cross product equations. So if we use our cross product, it's the same basic idea of we had these two equations for our cross product. We said A cross B is equal to the magnitude of A, magnitude of B, times sine of theta AB, times that unit normal vector in the direction perpendicular to the two. Well, we also said that A cross B is equal to our 3 by 3 determinant, where we had our unit vectors in the first row, ux, uy, uz, and then we had our vector components, ax, ay, az in the second row, and bx, by, and bz in our third row. And so what we're going to do again here is we're going to just equate our two right-hand sides. So we're going to say this is equal to this whole determinant here. And so going ahead and doing that and plugging in values, so for our determinant, we of course have just these unit vectors up top, ux, uy, uz, and then plugging in for our ax, ay, and az components, we have 3, 4, and 1. And for our b components, we have 0, 2, and negative 5. And now we know this is equal to AB sine of our theta AB times our unit normal vector u sub n. Now we've already solved for our values for magnitudes A and B, and we'll come plug those in a little later. But let's go ahead and evaluate this 3 by 3 determinant. So using the technique we saw in a previous video, we can say that this is negative 20 minus 2 in our x direction, plus 0 minus a negative 15 in our y direction, plus 6 minus 0 in our z direction. I switched things up a little bit on how I evaluated this middle term compared to the previous video. If you have questions about that or 3 by 3 determinants in general, again, please feel free to ask me and I'll be happy to help. So that's how we evaluate that 3 by 3 determinant. We now set that equal to our AB sine of theta AB times unit vector u sub n. Okay, well of course we can evaluate that, but what we want to do then is we're ultimately going to want to take the magnitude of both sides to get rid of that unit vector term on the right. So we have negative 22 in our x direction, plus 15 in our y direction, plus 6 in our z direction is equal to AB sine of theta AB times u of n. So now what we can do is take the magnitude of both sides. So magnitude of both sides, and what that's going to give us then is we'll have on the left side the square root of negative 22 squared plus 15 squared plus 6 squared is equal to AB sine of theta AB. So on the right, we just get rid of that unit vector u sub n. So of course now we can solve for that theta AB. Remember, we have solved for this magnitude A and magnitude B when we were doing our dot product method. So we can say theta sub AB is equal to the inverse sine of, and that product over here on the left ends up being the square root of 745, just to sort of keep things exact. And then in the denominator from our previous method with dot product, we had magnitude of A was square root of 26, magnitude of B was square root of 29. Plugging all of that into a calculator, we get approximately 83.728 degrees, which of course is the same angle that we got with our dot product, which we would expect.